330 billion solar masses, a star formation rate of less than 1 per year. The galaxy was already dead when the universe was 1.8 billion years old. Its designation is XMM, VID 1 2075, not a name designed to inspire awe. A catalog entry, a string of characters pointing to a patch of sky observed by the James Webb Space Telescope. What JUST found there raises a question no current model of galaxy formation can answer. How did a galaxy this massive, this stable, this quiet come to exist when the cosmos was barely old enough to produce one? The measurements do not allow for error. The timeline does not permit it. The universe is 13.8 billion years old. XMM VID 1-2075 sits at redshift Z equals 3.449. The light arriving from it has been traveling for approximately 12 billion years. What JUST captured is not the galaxy as it exists now. It is a portrait frozen in time, showing the structure as it appeared when the universe was only 1.8 billion years old, roughly 13% of its current age. Compress the entire history of the universe into a single calendar year. January 1st, the Big Bang. By early February, XMM VID 1-2075 had already finished forming. Earth would not coalesce until September. Humans would appear in the final seconds of December 31st. February. The galaxy was done by February. Standard cosmological models describe early galaxy formation as violent, chaotic. Gas collapses into dark matter halos. Smaller structures merge. Angular momentum from infalling material spins the resulting systems into rotationally supported disks. Stars ignite at furious rates, tens, hundreds of solar masses per year. Every simulation we have built describes the early universe as a construction site, messy, loud, unfinished. XMM VID 1-2075 is none of those things. JOST's near-infrared spectrograph measured the motion of stars within the galaxy. Stellar velocity dispersion, 379 kilometers per second. For comparison, the velocity dispersion in the Milky Way solar neighborhood is roughly 30 kilometers s. The stars in XMM VID 1-2075 are not orbiting in an orderly disk. They swarm in random directions, held together by an enormous gravitational well. This is the kinematic signature of a pressure-supported system, a dynamically relaxed elliptical galaxy, the kind of structure that, in the local universe, takes billions of years of mergers and heating to produce. This galaxy did not have billions of years. It had fewer than 2. The star formation rate confirmed by the Keck Observatory's Moss-Fire spectrograph sits below 1 solar mass per year. The Milky Way currently produces about 2 solar masses of new stars annually. XMM VID 1-2075 is quieter than our own galaxy, and it reached that silence 12 billion years ago. It is not forming stars, it is not assembling, it is done. The timeline had to be confronted directly. To reach 330 billion solar masses by the time we observe it, the galaxy would have needed to sustain formation rates of roughly 183 solar masses per year, every year, from the moment the first stars could form until the moment it stopped. There is no spectral evidence of such extreme activity in its history. The math does not resolve cleanly. Either XMM VID 1-2075 formed stars at a rate we have never observed and then abruptly ceased, or our understanding of how mass assembles in the early universe contains a gap we have not yet identified. The measurements are not in dispute. Keck confirmed the quiescence. JOST confirmed the kinematics. Archival X-ray data from XMM Newton and Chandra established the galaxy's high energy properties. Multiple instruments, multiple observatorias, consistent results. This is not instrumental error. This is not a statistical anomaly. XMM VID 1-2075 behaves as though it is billions of years older than the universe would have allowed. The data, across every platform that has observed it, agrees. What remains unanswered is the mechanism. Something caused this galaxy to assemble 330 billion solar masses, dynamically relax into a pressure-supported configuration, and shut down star formation, all within a window so narrow that our best simulations cannot reproduce it. The question is not whether XMM VID1 2075 challenges the standard model of galaxy formation. It already has. The question is what it reveals about the physics we are still missing, in the behavior of dark matter, in the efficiency of early star formation, in the very structure of the young universe itself. JOEST's spectral data holds the first clues. The data chain begins with light that has traveled 12 billion years, arrives at a mirror 6.5 meters wide, and splits into wavelengths. WST's near-infrared spectrograph, NIRSpec, does not take pictures, it dissects light. Each photon from XMM VID1 2075 passes through a diffraction grating and spreads into a spectrum, a barcode of absorption and emission lines that encode motion, temperature, composition. Astronomers measured the Doppler shifts embedded in that spectrum, the stretching and compression of wavelengths caused by stars moving toward or away from the observer. Map those shifts across the galaxy structure, and you obtain the stellar velocity dispersion, how fast stars are moving in random directions relative to one another. The measurement returned 379 kilometers per second. In the Milky Way's solar neighborhood, that number is 30 km/s. Stars orbit the galactic center in relatively orderly paths. Their random motion is modest, a perturbation on top of coherent rotation. XMM VID1 2075 stars move more than 12 times faster. This is not the signature of a galaxy still assembling through ordered spin. It is the signature of a system held together by an extraordinarily deep gravitational well, the kind found in massive, dynamically relaxed elliptical galaxies that, in the local universe, required billions of years to reach that state. A galaxy observed at cosmic dawn already exhibits the internal dynamics of a structure we would expect to find 10 billion years later. Confirmation arrived from a second observatory. The W.M. Keck Observatory's Mossfire spectrograph, the multi-object spectrometer for infrared exploration, positioned at 4,145 meters elevation atop Mauna Kea in Hawaii, targeted XMM VID 2075 to measure its star formation rate. Mossfire operates in the near-infrared, where emission lines from ionized hydrogen trace ongoing stellar birth. If a galaxy is actively forming stars, those lines glow brightly. In XMM VID 2075, they were nearly absent. The measured star formation rate, less than 1 solar mass per year. The Milky Way currently produces approximately 2 solar masses of new stars annually. A galaxy containing 330 billion solar masses, several times the stellar content of our galaxy, was forming stars at half our rate. The furnace had gone cold. 2 instruments, 2 observatories, the same conclusion. Cosmological simulations of the early universe make specific predictions about what massive galaxies should look like at redshift Z to 3.5. They should be rotationally supported. Gas falling into dark matter halos carries angular momentum. As it collapses inward, conservation of that momentum produces rotation. The result, a spinning disk, chaotic and clumpy, rich with star-forming regions, structurally dominated by ordered circular motion. XMM VID1 2075 shows none of this. Instead of rotational support, it exhibits pressure support. The random motions of its stars, rather than coherent rotation, prevent gravitational collapse. This is the dynamical signature of a giant elliptical galaxy, the kind found at the centers of massive galaxy clusters in the present-day universe. Such galaxies reach this state through a process called violent relaxation, in which mergers and gravitational interactions scramble stellar orbits over extended timescales. How extended? In standard models, the transition from a rotationally supported disk to a pressure-supported elliptical typically unfolds across several billion years. XMM VID 1-2075 appears to have completed this transition within 1.8 billion years of the Big Bang. The timeline compression is not marginal, it is fundamental. The stellar mass compounds the problem. Assembling 330 billion solar masses by the epoch we observe requires sustained, intense star formation across the galaxy's entire prior history. Divide the total stellar mass by the available time. The result is a minimum average formation rate of approximately 183 solar masses per year, maintained without interruption from the earliest moments of the galaxy's existence. The spectral energy distribution shows no evidence of such extreme rates persisting into the observed epoch. No starburst signatures remain. No massive reservoirs of heated dust glow in the infrared. The alternative, that star formation was even more concentrated, burning through available gas in a shorter, more violent burst before abruptly quenching, demands a shutdown mechanism of extraordinary efficiency, and no obvious candidate presents itself. Archival X-ray data from XMM Newton and the Chandra X-ray Observatory provided one potential answer, then eliminated it. Active galactic nuclei, supermassive black holes, violently accreting matter are the most commonly invoked quenching mechanism in massive galaxies. Their energetic outflows heat surrounding gas, preventing it from cooling and collapsing into new stars. XMM VID 1-2075 shows no X-ray signature consistent with a powerful ANG. Whatever silenced this galaxy, it was not the mechanism astronomers most frequently rely upon. JWST's imaging confirmed the morphology: compact, dense, structurally consistent with a quiescent elliptical. Not a disk, not a merger remnant caught mid-collision. A finished object sitting in the young universe as though it had arrived billions of years ahead of schedule. The measurements are clear. Every instrument agrees. The implications remain unresolved. If X-Minitive Vid 1-2075 assembled this much mass, relaxed this completely, and quenched this thoroughly within 1.8 billion years, it followed a formation pathway that no current simulation predicts. The question is no longer whether this galaxy exists in defiance of expectation. It is what permitted the early universe to build it this way, and whether the answer lies in physics we have not yet understood. Galaxy formation theory rests on a framework called hierarchical assembly. Small structures coalesce first, clumps of dark matter no larger than dwarf galaxies, and over billions of years these fragments merge, accrete gas, and gradually build the massive systems we observe in the local universe. Dark matter halos collapse under gravity, gas cools and spirals inward, stars ignite in waves. The process is slow, violent, and deeply dependent on time, producing a massive elliptical galaxy, the kind with hundreds of billions of solar masses. Low rotation, high velocity dispersion typically requires 8 to 10 billion years of mergers, feedback cycles, and dynamical relaxation. XMM VID 1-2075 appears to have completed this process in less than 1.8 billion. The first proposed explanation centers on an extraordinarily efficient starburst. If the galaxy converted gas into stars at extreme rates, far exceeding 183 solar masses per year, sustained across hundreds of millions of years, it could, in principle, have assembled 330 billion solar masses within the available window. Supernova feedback, or complete gas exhaustion, would then have quenched formation, leaving the system dormant. The problem is precision. Such a scenario demands that conditions align with almost mechanical efficiency: the right gas density, the right cooling rate, the right timing of quenching. No known mechanism produces this fine-tuning reliably. Simulations that attempt to replicate it consistently overshoot, either forming too many stars too late or failing to halt star formation at the observed epoch. The window is too narrow, the tolerance is too tight. The second hypothesis reaches deeper. What if dark matter itself behaved differently in the early universe? If halos at high redshift collapsed more rapidly or more completely than lambda CDM predicts, they could have funneled baryonic matter inward, with greater efficiency, compressing the assembly timeline. However, modifying dark matter halo collapse rates at Z to 3.5 creates tension elsewhere. The cosmic microwave background, mapped in extraordinary detail by the Planck satellite, constrains the growth rate of structure in the early universe. Altering halo dynamics enough to produce XMM, VID1, 2075, risks contradicting those constraints. The model begins to fracture at the edges. A third possibility involves early major mergers. If two or more already massive galaxies collided before Z equals 3.449, the event could have triggered a simultaneous starburst and dynamical heating. Angular momentum would cancel during the collision, producing the slow rotation observed. Violent relaxation, the process by which gravitational interactions redistribute stellar orbits, would generate the high-velocity dispersion of 379 kilometers s. This explanation is elegant, but it carries an uncomfortable implication. For massive galaxies to merge at z equals 3.449, they must have already existed at even earlier epochs. The problem does not disappear. It migrates backward in time. Consider the arithmetic once more. At 330 billion solar masses, XMM VID1 2075 contains roughly 3 times the stellar mass of the Milky Way. Our galaxy required approximately 13 billion years to reach its current mass of around 100 billion solar masses, and it is still forming stars at a rate of roughly 2 per year. By contrast, XMM VID1 2075 achieved triple that mass in roughly 1/7 the time, then stopped entirely. The ratio between assembly speed and final mass has no analog in current simulations. What compounds the tension is the galaxy's dynamical state. A velocity dispersion of 379 kilometers, S does not merely indicate large mass. It indicates that the system has thermalized, that stellar orbits have randomized through gravitational interactions over a timescale that, in the local universe, requires several billion years. XMM VID1 2075 achieved this relaxation when the cosmos was still assembling its first large-scale filaments. The dynamical maturity arrived before the cosmic infrastructure that supposedly enables it. This is where the discovery graduates from anomaly to crisis. If XMM VID1 2075 is unique, a statistical outlier, a 1 in a trillion event, then models can absorb it as an extreme tail of the distribution. Unusual, but not paradigm-breaking. However, early archival searches suggest it may not be alone. Other massive quiescent candidates at comparable redshifts have been tentatively identified in deep survey fields, though none yet confirmed with spectroscopic precision matching JWST's NIRSpec data. Should even a small population of such galaxies exist at z greater than 3, the standard lambda CDM timeline for structure formation would require fundamental revision, not adjustment, revision. 3 lines of evidence meet at a single point. A galaxy holding 330 billion solar masses, observed at redshift Z equals 3.449, has stopped making stars. Its velocity dispersion, 379 kilometers per second, confirms internal pressure support, dynamically relaxed, gravitationally settled. The structure resembles elliptical galaxies that required 10 billion years to form in the local universe. XMM VID1 2075 reached that state in less than 1.8 billion. The central question posed at the beginning now has an answer. It is not a comfortable one. The standard hierarchical assembly model, as currently formulated, contains no pathway capable of producing this object. The galaxy did not violate physics. It revealed a gap in our description of physics. Somewhere in the sequence, dark matter halo collapse, gas infall efficiency, early quenching mechanisms, there exists a channel of galaxy formation that no simulation has reproduced. XMM VID1 2075 is not an outlier to be explained away. It is direct observational evidence that the processes governing the first 2 billion years of cosmic structure formation operated with greater efficiency or through fundamentally different mechanisms than models predict. This matters beyond one galaxy. Archival searches have surfaced tentative candidates, other massive, quiescent systems at comparable redshifts, buried in deep survey fields, none yet confirmed with the spectroscopic precision JWST's NIR spec delivered for X-millimeter Vid1 2075, but their presence, even as candidates, changes the problem. A single object can be dismissed as statistical noise. A population cannot. Should further observations confirm even a modest number of similar galaxies at Z greater than 3, the frequency alone would exceed lambda CDM simulation predictions by orders of magnitude. The implication cuts deep. Either baryonic physics in the early universe, the cooling, collapse, and ignition of ordinary matter into stars, was dramatically more efficient than assumed, or dark matter halos assembled faster than the current power spectrum of density fluctuations allows. Neither adjustment is minor. Both propagate outward through cosmological models calibrated on decades of lower redshift data. The observational campaign has already begun. JWST Cycle 2 and Cycle 3 programs include targeted spectroscopy of high redshift massive galaxy candidates identified in COSMOS, GOODS, and UDS survey fields. Each confirmed detection adds weight. Each non-detection constrains the population size. Ground-based follow-up from Keck's Mossfire and the Atacama Large Millimeter Array will probe molecular gas reservoirs. The goal: measure whether these galaxies truly exhausted their fuel or whether some other process heated the gas beyond the threshold for collapse. The distinction is not academic. Gas exhaustion implies runaway early efficiency. Gas heating implies an external or feedback-driven quenching mechanism that current models underestimate. XMM VID1 2075 alone cannot distinguish between these scenarios. A sample of 10 such galaxies could. Simulations face a recalibration challenge. For 2 decades, cosmological hydrodynamic codes, Illustris TNG, Eagle, Simba, have been tuned to match the galaxy population at Z less than 2. Their success at reproducing local galaxy properties earned confidence, but calibration on local data carries an implicit assumption that the physics encoded in the simulations scales correctly to earlier epochs. XMM VID1 2075 suggests otherwise. The early universe may have hosted conditions, denser gas environments, more efficient cooling channels, faster halo mergers that only become apparent when instruments achieve the sensitivity to detect quiescent galaxies at Z greater than 3. Prior to JOST, such detection was technically impossible. The absence of evidence was mistaken for evidence of absence. XMM VID1 2075 will serve as a benchmark for the next generation of cosmological models. Theorists must now produce simulations that generate massive, quiescent, pressure-supported galaxies within 1.8 billion years of the Big Bang, without breaking agreement with the cosmic microwave background, large-scale structure surveys, or the observed properties of galaxies at lower redshifts. That constraint is severe. If achievable through parameter adjustment alone, the standard framework survives, refined. If not, the framework requires new physics, modifications to dark matter behavior, star formation prescriptions with no precedent in current theory, feedback mechanisms we have not yet conceived. The galaxy provides a binary test. Models either produce it or they fail. The universe built XMM VID1 2075 in conditions we have not yet learned to simulate, and it did so 12 billion years before anyone was watching.